This next section is going to talk about charge-coupled devices. Basically, that is digital cameras. To get started with this, the one thing we did not cover in electricity and magnetism as far as a device is a capacitor. So a capacitor will be a device that stores potential energy in an electric field. So what that means is that you have these two plates here, and we'll build up two different types of charge on these plates, and then what you do is you create this little electric field in between them, all right? And this, ends up building up some amount of voltage. So literally, all right, capacitance, which is the measure of how much charge can be put on a plate to build up a certain potential difference between them, all right? That kind of summarizes the whole idea there. So I'll write this again. How much charge must be built up or must be put on plates to produce a certain potential difference between them. Okay, so what this tells us is that capacitance is charge built up per potential difference. All right, we call this a farad. And so a farad is just the same thing as a coulomb per volt. Okay, so it's capacitors. These are vital in circuits, in really any type of circuit. Refrigeration, electronics, everything. It's really important because it helps to create an effect in a circuit that's almost like a dampener, I believe. Right. So, yeah. To do a quick example here, the potential difference measured across a 100 picofarad capacitor is 25 millivolts. We want to determine the charge and number of electrons stored in the capacitor. All right. So, it's pretty much capacitance here is this. We use this unit picofarads here. So this is how much charge we're pretty much building up. We're trying to figure out how much charge we're building up, okay, in the capacitor to create this, all right, on this negative side. So see here, that's the capacitance, the voltage that is built up between the two plates or whatever kind of capacitor it is 25 millivolts. So we just want to know the charge, and here the charge can be found by multiplying the capacitance times the voltage, and what we end up getting is going to be 2.5, let's see here, picocoulombs with the charge, okay? And then from there we could figure out the number of electrons simply by dividing this number by 1.6 times 10 to the negative 19 coulombs. So the number of electrons is 2.5 times 10 to the negative 12 divided by 1.6 times 10 to the negative 19. And when we do that, I just want to do this calculation really quickly. I haven't done it yet here. All right, so unfortunately, there we go. Sorry, guys. There we go. Number of electrons would be about 15, or 1.5625 times 10 to the 7th. All right, so about 16 million electrons there. All right? Sorry about that, just had to quickly do that math on the calculator. All right, so why do we care about capacitors? Why is it important that we can build charge up in a component in a circuit? Well, it turns out that there was this couple of guys at Bell Labs a little while ago, and what they were able to do, okay, and this is on your note page there, all right, was develop something called a charge-coupled device, okay. So the physical premise on this, all right, is that charge would be built up on one side of the device, all right, and because charge would be built up, it would create if that side of the device was part of a capacitor, it would also create a voltage. And that voltage that would be built up could be sent in as a signal to tell how much charge had been built up on that side of that capacitor. Okay. So the important thing here is, all right, is you have these charge-coupled devices, these little blocks. You can think of them like solar panels, okay, effectively in a certain way. And you have a photon of light come in, okay, and it hits this little guy right here. What happens is that it knocks out an electron, okay? So you have all these electrons built up over here. Now what these are is that they're also capacitors, okay? So when we knock out electrons, okay, we build up charge. Since they are capacitors, each square has a voltage associated with it, okay? So each of these little blocks, what they end up coming to be known as, all these are pixels. And if you have a certain type of pixel that's sensitive to a certain type of light, you know that that square will have built up so much charge, or in other words, it will have absorbed so much of a certain type of light. Okay? And effectively, this is how a digital camera works, is that this is the exact physical mechanism, all right? So on a typical digital camera these days, I don't know, I mean, how many megapixels are there? Mega, remember, that's millions. I know some digital cameras are 14, 16, probably even more these days, which is, an incredible amount. So let's do some problems here, okay, just some examples. And really quickly, on the next page there, it talks about image capture with a charged coupled device, okay. Once we have each square as a voltage, by the way, okay, an electrode, okay, measures the voltage and location of the pixel. All right, and that's how this charge-coupled device works. We'll talk about it a little bit more in class. All right. So if the height of the 6 megapixel CCD is 6 millimeters, okay, how big is 1 pixel? All right. So to find the area here, really quickly, okay, what you can do is just square 6 millimeters, so area is just going to be 6 times 10 to the negative 3 meters. Just square that. So it's going to be equal to 3.6 times 10 to the negative 5 square meters. All right. So the question then is that if we take this 6 million pixels and divide it by this, we can get an idea of the area of 1 pixel. So the area of 1 pixel, right? 3.6 times 10 to the negative 5 meters squared divided by 6 times 10 to the 6th pixels. So each pixel is just 6 times 10 to the negative 12 meters squared. Okay. And yeah, so I mean that's one way you can do it as far as finding the area. We can also try to figure out the actual dimensions of each pixel if we want to do that. Okay. So what we can find is that if we assume that this is a square, this would just be a continuation from number 2. Okay. So in other words, if it's 6 megapixels in terms of the total number of pixels in here, how many pixels make up one side here? This is going to be the square root of 6 million pixels. Okay, so this number is just this right here. Kind of a messy number, all right? And so you can just divide the length of one side by this, and this will give you the length of one side of the pixel, which is just 2.4 micrometers. So each of these pixels is incredibly small. That's approximately the size of each side. All right? So that gives you an idea right there of the size of a pixel. Come back here. If photons are incident, okay, we have some amount of lights incident on a 5 megapixel camera CCD, all right, at this rate, how many photons land on each pixel in 15 milliseconds, okay? So again, we have 5 times 10 to the 6th pixels, okay? So we're dividing this rate right here, okay? And actually, you know what, let's first figure out how many total photons we're going to have landed here. So it's 2 times 10 to the 8th pixels per second times 15 times 10 to the negative 3 seconds. So that's going to give us 3 million photons that will have landed on the CCD. And if we want to know the number of photons per pixel, we're just going to divide that by the number of pixels here. So we get this right here. 0.6 photons per pixel, all right? Very dim picture. Okay, so if the rate of reading each pixel in the serial register, okay, so this is the thing that's going to be taking down the voltage and location of each pixel, all right, is 5 megahertz, how long will it take to read all of the pixels? Well, if it's 5 times 10 to the 6th pixels, all right, and we are reading at a rate of 5 times 10 to the 6th pixels per second. Okay, that's what the hertz means there, cycles per second. I mean, here's an example where hertz can mean this, okay? That means that we're going to need 1 second, all right, for that picture to be stored in whatever digital format, okay? All right, so it turns out that CCDs, the surface is not perfect at absorbing photons. So we have a measure of how well the surface can absorb photons. We call it quantum efficiency. All right. So what it is that it's the number of absorbed photons per the number of incident photons. All right. So the formula that we can use is just this. If a photon has been absorbed, we assume that it emits an electron. So emitted electrons divided by incident photons okay, it will give us the quantum efficiency. So for example, all right, let's say that a certain X-ray machine uses CCD that we know the quantum efficiency here, any efficiency we can call E here, right? Is going to be 85%, 0.85. Okay, determine the number of X-ray photons needed to build up a charge of 7.2 nanocoulombs. All right, on 1 pixel in the CCD array. Okay. So what we're looking for here is the charge is going to be built up to 7.2 nanocoulombs, right? And so each photon, we're going to assume that there's an electron associated with it. So the total number of electrons that we're going to need here is just going to be that charge divided by the charge of an electron. So this right here. All right, which means that we would need about 45 billion electrons. All right, so quantum efficiency here is going to be equal to the number of emitted electrons divided by the number of photons. And so we're just solving for the number of photons, really, which is the number of electrons divided by the efficiency. And that's just going to be 4.5 times 10 to the 10th all over 0.85. And when you solve that, you end up with this many photons. Just a few more notes here, okay? So what is an advantage of using a CCD with a higher quantum efficiency? Well, with the camera, you need less exposure time, which is good if you need a shot of a fast-moving object. Okay. And you can photograph dimmer objects. That's the other good piece of this. All right. So there's a good practice problem here. Quantum efficiency of the pixels in a certain CCD is 40%. How much potential difference is built up across a single 35 picofarad pixel in 5 milliseconds if photons are incident on it at a rate of 4.5 million per second? Okay, so let's write all this out here. Rate which we're getting photons in here is going to be 4.5. So the total number of photons in this case, right? I'm just going to go straight and convert this because we only need the number of photons. We don't have to worry about the rate here. Okay, it's going to be the rate there, 4.5 million photons falling per second times 5 milliseconds, which is just going to give us 22,500 photons. All right. And the capacitance here is, let's see, 35 times 10 to the negative 12, because 10 to the negative 12 is at pico farads. All right. What we're also given is the quantum efficiency, okay, which is 0.4. So what we need, we want the voltage, so we need the charge, okay, and we can get the charge because we can get the number of emitted electrons here from the number of photons in the quantum efficiency, okay, so this is going to be 0.4 times this 2.25 times 10 to the fourth. And once we know the number of electrons, we can get the amount of charge, okay? So the charge here is just going to be equal to E times N sub E, right? 1.6 times 10 to the negative 19 coulombs. And the charge that we're getting here is this. Bring this back up here to our equation for the voltage related by capacitance and charge. And what we end up with is a small little voltage that we put up on this little pixel. And so that answer, we know this answer makes sense because of how small the voltage is that we're building up in the pixel. I mean, it shouldn't be a large amount. Okay, that's it. So yeah, that's a good example of a question you may be asked on an IB test for CCDs. So if you want to try number 7 on your own, that would be good. All right, we will do it in class. I will give you the answer right now. All right, and the voltage you should end up with, the potential difference across the pixel, should be 6.0 times 10 to the negative 5th volts. All right, and in the next video, we'll talk about magnification and resolution with taking pictures from CCDs.